Swayam Prabha. Digital India. Educated India.
Okay, so now we will continue with the theory of optimization that we have been building up so far. So what we learnt in the previous lecture was we basically proved this theorem, that consider the optimization problem minimize fx subject to gi of x less than equal to 0 for all I from 1 to m, where f and g1 till gm, these are all C1, and let x star be a local minimum, and suppose that a constraint qualification is satisfied at x star. Okay. Then there exists lambda I greater than equal to 0 for all I in A of x star, such that gradient of f at x star plus the sum of lambda I gradient of gi of x star over all I in A of x star equals 0. Okay. Where now A of x star, recall, is the active set. It is those i's for which gi of x star is equal to 0. Okay. So this is what we derived last time. This condition is was called the KKT condition, okay, due to Karush, Kuhn and Tucker, and the lambdas here are called the Lagrange multipliers. Okay. Now you can, what we will do now is we can generalize this a little bit. We can write the same condition here in a slightly different way. We can see if you have, suppose if you have two, we can write this condition here in the following form. We can say, let us consider this summation, which is now only over A of x star, okay, only over the active set. Let me write this summation in the following way. I will write grad f of x star plus sum over lambda I gradient of gi of x star, and the sum is now over all I going from 1 to n. This is equal to 0. But then in addition, what I will do is I will put a condition that says that lambda I equals 0 if gi of x star is less than 0. So it says, this condition simply says that lambda I is equal to 0 if your constraint is not active. So then what it means is, effectively, or as a result, this sum here, which is over all the constraints I from 1 to m, will reduce to just a sum over the active constraint. But you can see what has happened as a result. We have now got back this condition that we have seen as part of linear programming. I had to, a couple of lectures ago, I told you that there is this condition which simply which says that this variable, the Lagrangian, there is a variable of the dual problem which must be 0 if a particular constraint is not satisfied with equality, if the corresponding constraint is not satisfied with equality. And this condition was what we call complementary slackness. So, this complementary slackness in the case of general optimization, not just linear optimization, is precisely this condition. It says that if the constraint is not active, then the corresponding value of the Lagrange multiplier must be 0. Okay. So, as what this effectively says does is it asks us to now look for says that if you want to solve look for a necessary condition for a point x star to be a local minimum, what you need to solve for are, you need to make sure that your constraints are satisfied, and you need to look for m Lagrange multipliers, lambda 1 to lambda m, so that the KKT conditions hold. But now the KKT conditions are linear in lambda, but may be non-linear in x star. But in addition to the KKT conditions, we have to also satisfy complementary slackness, meaning that you need lambda I to be equal to 0 if gi of x star is less than 0. Okay. So, what's the point of writing it in this way? What's nice about it is that now when I try to solve the KKT conditions, I don't have this x star sitting in this summation here. The x star which is telling me the indices involved in the summation, that kind of dependence is now gone, and now my summation is over all I from 1 to m. But a complication has now arisen that now I need to make sure this new condition, which is complementary slackness, that needs to be satisfied, right. So, KKT conditions will now involve one nonlinear equation like this, which is this one, and in addition to that a complementary slackness condition, which is this. Now, complementary slackness itself we can simplify and write in a nicer form. We can say complementary slackness can be written in this sort of form, that for all I, lambda I into gi of x star is equal to 0. Lambda I times gi of x star equals 0. Now, this should be true for all I, not just for the ones that are not active. This is true for all I. The ones that are for the i's that correspond to active constraints, gi of x star will be equal to 0. For the ones that are not active, it necessarily means that lambda I must be equal to 0, right. So, since the product of these two is equal to 0, at least one of them must be 0. So, which means that if your GIs, if your constraint ith constraint is active, then I don't care what the Lagrange multiplier is, so long as it is greater than equal to 0 as written here. And if my constraint is not active, then I have no choice but to make sure that my Lagrange multiplier is 0, right. So, the way KKT conditions are often written then is in this sort of comprehensive form. You have gradient of f from I equal to 1 to m lambda I gradient of gi star equals 0, and you have lambda greater than equal to 0, gi of x, lambda I greater than equal to 0, gi of x less than equal to 0, I running from 1 to m, and you have lambda I times gi, x star here, sorry, lambda I times gi of x star equals 0. So, these are your KKT conditions. Okay. Now, you can see what has happened in this sort of problem because of the nature of inequality constraints. The whether a term will appear in this first equation here, in this first equation, whether the ith the gradient with respect to the ith constraint is going to appear or not will depend on the x star you are considering, because after all that only terms that appear there are the ones that are active. So, it will depend on the x star that you are considering. So, if it appears, then this particular so which means if your x star which means if your thing, if your constraint is active, then you do not need to worry about this complementary slackness condition, and lambda I, only thing you need to worry about is making sure lambda I is greater than equal to 0. But if it does not appear, then what you are effectively doing is putting lambda I equal to 0. So, essentially solving a optimization problem with inequality constraints involves basically first trying to check which constraints are actually active, because once we define the active constraints, then the A of x star gets fixed, and then we can hope to just simply solve this equation, this nonlinear equation. Without the active constraints having first been determined, it becomes very hard to do that. So, there are many, implicitly in an optimization with inequality constraints is this effort to try and make a combinatorial choice out of the m constraints, which k are actually active. We are trying to always decide the set of active constraints either directly or indirectly. Directly means that you actually try to keep searching over active constraints, or indirectly means that you somehow try to discover them through complementary slackness, meaning through this condition. Okay. So, remember this, that optimization problems with inequality constraints have basically a combinatorial flavor to them, because the nature of the problem changes from whether the constraint is active or not active. If it is not active, essentially the tangent cone is Rn, you do not need to worry about, you have plenty of room around a particular point to see what to perturb the function and to perturb the point. Whereas, if your constraint is active, then the nature of the problem changes, because you are constrained to move only in certain types of directions. Okay. All right. So, now let's add a little bit of for completeness sake, let us add a little bit of complexity here. So, let us consider this problem, minimize function f subject to gi of x less than equal to 0 for all I from 1 to m, and also hj of x equal to 0 for all I from 1 to p. For this sort of problem, what we can do is, we can simply look at the constraint hj of x equal to 0 as being two opposing inequalities. So, minus hj of x less than equal to 0 and hj of x less than equal to 0. With these two opposing inequalities, we can again write out the tangent cone conditions, write out the KKT conditions, and what that would give us is, you would now get a Lagrange multiplier for this constraint, and you will get a Lagrange multiplier for this constraint, right. So, suppose the Lagrange multiplier for this constraint is mu j, and the Lagrange multiplier for this constraint is suppose nu j. So, then in that case, the KKT conditions will read as gradient of f at x star plus summation lambda I gradient of gi of x star I from 1 to m plus now summation nu j minus mu j gradient of Hj at x star, j going from 1 to p. Right. So, how did I get this? I just wrote out the KKT conditions from the previous slide, but now I considered in place of this equality constraint Hj of x equal to 0, I am going to consider an inequality constraint like this minus Hj of x equal to 0 and also Hj of x equal to 0. So, with the Hj of x equal to 0, I get a nu j as my Lagrange multiplier. With minus Hj of x, I have mu j as my Lagrange multiplier. So, I get nu j minus mu j. All right. Now, what we know is that both these Lagrange multipliers, nu j should be greater than equal to 0, mu j should be greater than equal to 0, just like lambda i's should also be greater than equal to 0. But then the difference here, nu j minus mu j, this may be positive or may be negative. This may be positive or negative, right. So, also it must be that either since eventually for a point to be feasible and since both these constraints must be satisfied, it has to be that for a point x star to be feasible, it has to be that Hj of x star is equal to 0. And so, consequently, any complementary slackness type condition is actually meaningless for this sort of constraint, because even if I put it, I would end up saying something like this: nu j into Hj of x star equals 0 and mu j into Hj of x star equals 0. This kind of condition automatically holds since Hj of x star itself is equal to 0. Right. So, as a consequence, two things happen. One is that whatever is multiplying this gradient of Hj cannot be constrained in sign. We cannot say it is greater than equal to 0 or less than equal to 0. And secondly, the complementary slackness conditions for Hj of x are automatically satisfied. So, the way we can summarize all this in terms of KKT conditions is to write that now the KKT conditions for this sort of problem, KKT conditions for this sort of problem are gradient of f at x star plus lambda I equals 1 to m plus, say, let me introduce another Greek character here. So, let us say theta I this equals 0, where now lambda I must be greater than equal to 0, gi of x star must be less than equal to 0. This is for all I from 1 to m. Hj of x star must be equal to 0 and lambda I times gi of x star must be equal to 0. There is no sign restriction on theta I. Theta I can be theta j, I should have written as theta j. So, there is no sign restriction on the theta j. Theta j can be positive, theta j can be negative, does not matter. Again, because there is also no reason to impose any complementary slackness, since Hj of x is already equal to 0. Okay. So, this what I have written here are your comprehensive KKT conditions for all kinds of optimization problems. So, any problem that can be written like this, and if you have that the constraint qualification is satisfied, then it must be that at x star all of these conditions, if x star is a local minimum, then these conditions must hold. That is what this means. Okay. All right. So, now what we can do now is ask the following question, that what if constraint qualifications are not satisfied, what if the KKT conditions hold, but but I don't know if I am at a, how do I know that I am at a local minimum, etc., etc. Okay. Before I do that, I forgot one thing. Let me mention this function L. This introduce just for you to remember. This function is what's called the Lagrangian. So, this function written with a fancy L is what is called the Lagrangian. It is a function of both x as well as the two Lagrange multipliers involved. The Lagrange multipliers for the inequality constraints, the Lagrange multipliers for the equality constraints. Right. So, the first equation therefore, in the KKT conditions are actually simply saying that if you take the Lagrangian and differentiate it with respect to x, the gradient so the gradient of the Lagrangian with respect to x must be equal to 0. That is what the first condition is saying. Sometimes people also write this second condition here, this second condition or this feasibility condition here, that Hj of x is less than or equal to 0. Sometimes people also write it as saying that gradient of the Lagrangian with respect to, sorry, this should not be mu, this should have been theta. The gradient of the Lagrangian with respect to theta is equal to 0. That is correct, because then if you take the gradient of the Lagrangian with respect to theta, it actually gives you Hj of x equal to 0, and put that equal to 0, you get Hj of x star should be equal to 0, which is precisely what is written here. However, you should be careful in not taking this too far. Do not, now if you take the gradient of the Lagrangian with respect to lambda, if you take the gradient of the Lagrangian with respect to lambda, so this should be at x star, what is that equal to? Well, that gradient of the Lagrangian with respect to lambda I, what that is equal to, what that is equal to is simply gi of x star, and this is not necessarily equal to 0. This could be 0, could be less than 0. If it is less than 0, well, then in that case the lambda I corresponding to it must have been 0. Alright. So, you have to be extremely careful in applying this particular thing, or where you take Lagrange multipliers, where you take gradients of the Lagrangian with respect to the Lagrange multipliers. So, there is, remember that there is no such thing with respect for the inequality constraints. You can use that kind of mnemonic if you like for the equality constraints only. So, now with this, let us now answer the questions of what happens if my KKT conditions are satisfied, or what if my constraint qualifications do not hold, and so on. So, if my constraint qualifications do not hold, can I say something about the problem? If my KKT conditions are satisfied, can I still say something about the problem? How can I know? I just know that the KKT conditions are necessary conditions. How do I know that? What can I say about anything about the point itself? So, so these kind of questions, let us try to answer them now. All of these questions basically come down, answering these kind of questions comes down to one key property, which is convexity. Okay, convexity is the heart of optimization, because it lets you reverse this chain of implications. So far the way we worked was, we said here is an optimization problem, suppose here is a local minimum, and if it is if here is a point x star, that is a local minimum, and we said if x star is a local minimum, then here is a condition that x star must satisfy. Now, if you wanted to go the other way around, where you suppose found a point x star which satisfies the KKT conditions, what can you say about x star? Is x star a local minimum? Is x star a global minimum, etc.? To answer these kind of questions, the key property that comes to use is convexity. So, So, when you have a convex optimization problem, this chain of implications can be reversed. Means that if you find an x star that satisfies the KKT conditions, then that x star is the solution of the optimization problem. No questions asked. It does not matter if your constraint qualifications hold or do not hold. It does not. You do not even have to check if that x star is a local minimum to begin with. You just simply solve the KKT conditions. Once the KKT conditions are solved, the problem is solved. All right. So, this is the beauty of convex optimization.